Hello and welcome. In this lecture, we're going to be talking about doing inference for estimators other than the mean of a distribution. Up to this point, we've been talking about how we use the sample mean and what the central limit theorem tells us about the sampling distribution of sample means to make inferences about a population mean. But there are lots of other things that the central limit theorem and this approach can tell us. So for example, up to this point we've been talking about questions like, in the distribution of women's heights in the United States, how can we use a sample to tell us the population mean of that distribution? But we can also use these same principles of the central limit theorem and generalizing from a sample to a population to tell us something like, what's the proportion in that distribution of US adult women's heights? What's the proportion of observations that fall between 5'5" and 5'7"? That will be an example of a sample proportion, and that sampling distribution is also something that's nearly normal when we have a sufficiently large sample. I do want to make sure to note that not all point estimates and not all sample statistics follow a nearly normal distribution, even when sample sizes are very large. For example, the sampling distribution of sample variances is not a nearly normal distribution, and so we can't use the techniques that we've talked about up to this point in the course to model that distribution. So when we use a point estimate to be our best estimate of a population parameter, we're making an important assumption that that point estimate is unbiased, which means that the sampling distribution of that estimate is centered on, has its mean at, the true population parameter that it is supposed to estimate. So an unbiased estimate does not overestimate the parameter or underestimate the parameter consistently. On average, it is centered on the real population parameter, so it's on average a good estimate. Doesn't overshoot, it doesn't undershoot consistently. So the sample mean is an example of an unbiased point estimate. This is a statistically proven concept that the sample mean is unbiased. So sometimes when we take a sample, the mean of that sample will be below the true population parameter. Sometimes when we take a mean of a sample, it'll be above the true population mean. But on average, that distribution is centered on the actual population mean. So that statistic is unbiased. We've talked about constructing confidence intervals, particularly for sample means before. I just want to reiterate here that anytime we're constructing a confidence interval around an unbiased and nearly normal point estimate, like we've been talking about, the confidence interval formula is the point estimate plus or minus our z level times the standard error. So remember that the z that we choose corresponds to our desired confidence level. So if we want 95% confidence, our z is 1.96, for example. And of course, SE in this formula is just the standard error, which we've talked about how to calculate in the past. So this confidence interval formula is generalizable to any unbiased and nearly normal point estimate. And this z star times SE parameter, that part of the equation is called the margin of error. Let's look at an example for hypothesis testing with an estimator other than the sample mean. In this case, we're going to be talking about the National Health and Nutrition Examination Survey, and particularly the data collected on body fat percentage and gender for 13,601 respondents. So the average body fat percentage for the men in the sample was 23.9%, and the average body fat percentage for the women in the sample was 35.0%. And we're going to go ahead and stipulate that the standard error for the difference between the male and female body fat percentages was 0.114. We want to know whether the data give us evidence that men and women have different body fat percentages on average. And we're going to go ahead and assume that the distribution of the point estimate is nearly normal. The steps for carrying out a hypothesis test are to specify our hypotheses, to calculate the point estimate that we're going to be checking, to make sure that the conditions that we need to do the hypothesis test hold, then draw our sampling distribution, make sure that we understand that, and then we're going to calculate our test statistic and p-value and make our determination about whether the null hypothesis or the alternative hypothesis better represents the data that we have. Our null hypothesis for this example is that the mean body fat percentage for men and the mean body fat percentage for women are equal, and the alternative hypothesis is that those means are different from one another. So the parameter of interest for us is the average difference in the means for the body fat percentages of men and women in the entire population. So the point estimate from our sample data that we're going to be using is the difference between the sample means for men and women in the sample that we have. So in this case, the sample mean for men is 23.9 and the sample mean for women is 35, and the difference between those is negative 11.1. Now remember, we need to have our point estimate be distributed nearly normally in order for these techniques that we're going to use to be valid. We're going to just go ahead and assume that that's the case for this sample. This is an assumption that we can test to some extent, and we're going to talk about that a little bit later in the course. But for right now, we're just going to note that we've got a pretty large sample, more than 13,000 respondents, and we know that theoretically the difference in sample means is something that should be normally distributed. So we're going to go ahead and assume that those conditions hold. So our null hypothesis says that the mean body fat percentage for men is equal to the mean body fat percentage for women. That's mathematically equivalent to the mean for men minus the mean for women being equal to 0. So our sampling distribution should have a mean of 0. And then to do our two-tailed hypothesis test, we're going to look out at the points in this distribution as extreme or more extreme than our observed value of negative 11.1. We're going to look at the area under the curve more extreme in both directions than those points. So the area under the curve as extreme or more extreme than negative 11.1 off to the left side of the distribution, and as extreme or more extreme than positive 11.1 off to the right side of the distribution. In this test, we're going to compute our z-test statistic in the usual way. We take our point estimate minus the null value divided by the standard error. So negative 11.1 minus 0 divided by 0.114 gives us a test statistic of negative 97.37. So that's a really big z-score. We've been looking at z-scores on the order of a z of 1, 2, 3, or 4. So a z-score of more than 97 is really huge, so our p-value is going to be really tiny. It's going to be approximately equal to 0, which tells us that under the null hypothesis, the probability of observing a difference in means as extreme or more extreme than what we observed is about 0. So that's really strong evidence that we should reject the null hypothesis in favor of the alternative hypothesis, or in plain English, that's really convincing evidence that the average body fat percentage for men and the average body fat percentage for women are different. They're not equal to one another. So the testing procedure that we've been talking about here and that we've used in previous lectures rests on this assumption that our sample statistic is distributed nearly normally. I want to be clear that we can still calculate confidence intervals and do hypothesis tests when our test statistic that we're looking at is not distributed nearly normally. And there are a couple of reasons why we might run into situations like that. We might have collected too small of a sample, or we might be dealing with a statistic that is just naturally not going to be distributed normally under any circumstances. So in each of these cases, where the normal approximation is not something that we can use, we're going to have to follow different procedures, and we're going to run into some of these examples later in the semester. But I do just want to be clear that we don't have to have normally distributed data or normally distributed sample statistics in order to use these basic concepts of hypothesis testing and confidence intervals. The statistical tools that we've been talking about rely on two basic conditions. The first is that the observations in our sample are independent, and that condition should be satisfied if we followed a random sampling procedure, or if we're doing an experiment, a random assignment procedure. If we don't meet this independence requirement, we're going to have to use some pretty advanced statistical methods. The other basic condition is that our sample size should be large enough for us to be able to do valid inference. In most applications, we're going to want a sample size of at least 30. And if the sample has too strong of a skew, or if there are too many extreme outliers, which are particularly a problem in small samples, those are also going to cause inference problems for us. So if those two conditions are not satisfied, if our observations are not independent, or if the sample is too small or too skewed, then you're going to have to either learn some new methods to model that data in particular. Another option is to consult somebody who has a better handle on those methods than you do. The thing that you don't want to do is ignore that those conditions aren't met. So if you don't have independent data, you shouldn't proceed with your analysis and just act as though you do have independent data, because that will make your inferences invalid and not reliable. So that's been our discussion on extending this hypothesis testing framework outside of the sample mean to population mean context. Thank you for listening, and I will see you next time.